Welcome to this rigorous scientific lecture on how hydrogen spectral lines forced us to accept quantized energy levels. Today we're going to walk through the actual historical workflow that led to one of the most profound discoveries in physics. In the mid-1800s, scientists discovered something puzzling. When you pass light from excited hydrogen gas through a prism, instead of seeing a continuous rainbow spectrum, you see only specific colored lines at precise wavelengths. This was completely unexpected. Classical physics predicted a continuous spectrum, but nature gave us discrete lines. Why? The first step in any scientific investigation is careful measurement. Let's measure the wavelengths of the visible hydrogen lines, which are called the Balmer series. Using a diffraction grating, scientists in the 1800s could measure these wavelengths with remarkable precision. Here are the measured wavelengths. The red line at 656.3 nanometers, the cyan line at 486.1, the blue at 434, and violet at 410.2 nanometers. Now here's the critical question that every scientist asks when looking at data. Is there a pattern? These numbers seem random at first, but let's investigate deeper. Step 2 is to find an empirical relationship. In 1885, Johann Balmer, a Swiss mathematics teacher, discovered a remarkable pattern. Balmer tried various mathematical relationships. He tested linear functions, quadratic functions, exponential relationships. Nothing worked until he tried something unusual. He found that 1 over wavelength equals a constant RH times the quantity 1 over 2 squared minus 1 over n squared, where n is an integer starting at 3. This is the famous Balmer formula. At this point, it was purely empirical. It fit the data beautifully, but nobody knew why. The constant RH, called the Rydberg constant, equals 1.097 times 10 to the 7 per meter. Let's verify this formula actually predicts the measured wavelengths. This is crucial in science. Any proposed relationship must match experimental data. For n equals 3, 1 over lambda equals 1.097 times 10 to the 7 times the quantity 1/4 minus 1/9. 1/4 minus 1/9 equals 0.139. Multiplied by the Rydberg constant gives 1.524 times 10 to the 6 per meter. Taking the reciprocal gives 656.3 nanometers. This matches the red line exactly. When you do this calculation for n equals 4, 5, and 6, you get the exact wavelengths for the cyan, blue, and violet lines. The agreement is extraordinary. Step 3 is the real test of any scientific model. Can it predict phenomena outside the range of the original measurements? Here's the question. If we use n equals 7 or 8, does the formula predict additional lines that we should be able to measure? For n equals 7, the formula predicts 397 nanometers, which is in the ultraviolet. And indeed, when scientists looked in the ultraviolet region, they found this line exactly where predicted. Even more remarkably, the formula generalized to other series. The Lyman series in the ultraviolet has 2 replaced by 1. The Paschen series in infrared has 2 replaced by 3. The general Rydberg formula is 1 over lambda equals RH times 1 over n final squared minus 1 over n initial squared, where n initial is greater than n final. So we have a perfect empirical formula that predicts every hydrogen line ever measured. But science demands more than just fitting data. We need to understand why this mathematical form appears in nature. Step 4 is where the breakthrough happens. In 1913, Niels Bohr proposed a radical hypothesis that seemed crazy at the time. Bohr proposed that electrons and atoms can only exist in specific discrete orbits with quantized angular momentum. Not any orbit, only special ones. The angular momentum L equals n times h bar, where n is a positive integer, and h bar is Planck's constant divided by 2 pi. This was shocking because in classical physics, an electron should be able to orbit at any distance with any energy. Bohr said no, only certain special orbits are allowed. Step 5 is to mathematically derive what energies these quantized orbits have. This requires combining the quantization condition with classical electrostatics. The electron experiences Coulomb attraction to the proton. The force equals Ke squared over r squared, where K is Coulomb's constant and E is electron charge. For a circular orbit, this force must equal the centripetal force, which is m versus squared over r, where m is electron mass and v is orbital velocity. Setting these equal gives ke squared over r squared equals m versus squared over r. Now we apply Bohr's quantization condition. The angular momentum, mvr, equals nh bar. From mvr equals nh bar, we get velocity equals nh bar over mr. Substituting this into the force equation and solving for r gives Rn equals n squared h bar squared over mke squared. The radius is quantized. For n equals 1, this gives 0.529 angstroms, called the Bohr radius. This is the smallest allowed orbit. Now we can calculate the total energy of each allowed orbit. The total energy is kinetic plus potential. The kinetic energy is 1/2 m versus squared, and the potential energy is negative ke squared over r. After substituting our expressions for v and r and simplifying, we get En equals negative mk squared e to the fourth over 2h bar squared n squared. Plugging in all the physical constants, this becomes En equals negative 13.6 electron volts divided by n squared. So the energy levels form a ladder. For n equals 1, E equals negative 13.6 electron volts. For n equals 2, negative 3.4 electron volts. For n equals 3, negative 1.51 electron volts. Each rung is precisely defined. Here's a visualization of the energy level diagram. When an electron drops from n equals 3 to n equals 2, it must emit a photon with exactly the energy difference. Step 6 is to connect these energy levels to the spectral lines. When an electron transitions between levels, it emits or absorbs a photon. The photon energy equals the initial energy minus the final energy. That's negative 13.6 over n initial squared minus negative 13.6 over n final squared. Simplifying gives 13.6 times the quantity 1 over n final squared minus 1 over n initial squared electron volts. Now we use the fundamental relationship between photon energy and wavelength from quantum mechanics. Energy equals h nu equals hc over lambda, where h is Planck's constant, c is speed of light, and lambda is wavelength. Setting our energy expression equal to hc over lambda gives hc over lambda equals 13.6 times 1 over n final squared minus 1 over n initial squared. Rearranging for 1 over lambda gives 1 over lambda equals 13.6 over hc times the quantity in parentheses. Now let's calculate that constant 13.6 electron volts divided by hc and see what we get. 13.6 electron volts equals 13.6 times 1.6 times 10 to the negative 19 joules. hc equals 6.626 times 10 to the negative 34 times 3 times 10 to the 8 equals 1.988 times 10 to the negative 25 joule meters. Dividing these gives 1.097 times 10 to the 7 per meter. This is exactly the Rydberg constant. This is extraordinary. Starting from the hypothesis of quantized angular momentum, we derived the exact empirical formula that Balmer discovered by trial and error. Step 7 is rigorous validation. Let's make quantitative predictions and compare to experiment. Let's predict the energy of the Balmer-alpha line, which is the transition from n equals 3 to n equals 2. E equals 13.6 times 1/4 minus 1/9 equals 13.6 times 0.139 equals 1.89 electron volts. Using lambda equals hc over E, with hc in convenient units of 1240 eV nanometers, we get 656 nanometers. Perfect agreement. Let's predict the ionization energy, the energy needed to remove the electron completely from n equals 1 to n equals infinity. E ionization equals 0 minus negative 13.6 equals 13.6 electron volts. Experiments confirm this exactly. Let's predict the Lyman-alpha line, the transition from n equals 2 to n equals 1. E equals 13.6 times 1 minus 1/4 equals 10.2 electron volts. This gives 121.6 nanometers, deep in the ultraviolet. This line was indeed discovered exactly where predicted. The real power of this model is that it predicted spectral lines that had never been measured before. Scientists then went and found them exactly where the theory said they should be. But here's the deep question. Why must energy be quantized? What forces nature to allow only certain discrete values? The answer came from de Broglie. Electrons have wave properties. For a stable orbit, the electron wave must form a standing wave that connects smoothly to its net. The circumference 2 pi r must equal an integer number of wavelengths n lambda, otherwise destructive interference destroys the orbit. The de Broglie wavelength equals h over momentum equals h over mv. Substituting gives 2 pi r equals nh over mv, which rearranges to mvr equals nh over 2 pi equals nh bar. This is exactly Bohr's quantization condition. So quantization is not arbitrary. It emerges naturally from the requirement that electron waves interfere constructively to form stable standing wave patterns. Let's do a quick back-of-the-envelope calculation to get physical intuition for the size of a hydrogen atom. The Bohr radius is h bar squared over mke squared. Let's estimate this using rough values. H bar is about 10 to the negative 34, electron mass is about 10 to the negative 30 kilograms, and ke squared is about 10 to the negative 28 in SI units. So R1 is approximately 10 to the negative 68 over 10 to the negative 58 equals 10 to the negative 10 meters, which is 1 angstrom. That's the right order of magnitude. Now let's estimate the ground state energy using dimensional analysis. The energy scale is ke squared over r, which is 10 to the negative 28 over 10 to the negative 10 equals 10 to the negative 18 joules. Converting to electron volts, 10 to the negative 18 joules is about 10 electron volts. This is the right order of magnitude for the 13.6 electron volts ionization energy. Let's summarize what we've learned. This is a beautiful example of the scientific method in action. First, we measured the precise wavelengths of hydrogen spectral lines and found they appeared only at specific discrete values. Second, we discovered an empirical formula, the Rydberg formula, that perfectly predicted all the measured wavelengths. Third, we validated the formula by predicting lines outside the original measurement range, like ultraviolet and infrared series. Fourth, we proposed a radical physical hypothesis that electron orbits are quantized. Fifth, we derived the discrete energy levels mathematically from the quantization condition, combined with classical electrostatics. Sixth, we proved our theoretical model reproduces the empirical Rydberg formula exactly, deriving the Rydberg constant from fundamental constants. Finally, we made new predictions, like ionization energies, and previously unmeasured spectral lines, all confirmed by experiment. The profound conclusion is that energy in atoms is quantized, not because we want it to be, but because nature forces it upon us through experimental evidence. Classical physics predicted continuous spectra with all wavelengths present, but hydrogen gives us only discrete lines. The spectral line data, combined with blackbody radiation and the photoelectric effect, force physicists to accept that nature is fundamentally quantum at atomic scales. This changed our entire understanding of physical reality. Energy, momentum, angular momentum all come in discrete packets at the atomic level. Today we use these quantum principles to build lasers, semiconductors, and quantum computers. All of modern technology rests on the foundation of quantized energy levels. You might ask, what about other atoms? Does this work for helium or carbon? The answer is yes, but it's more mathematically complex. For multi-electron atoms, electrons interact with each other, requiring the full quantum mechanical Schrödinger equation. But the fundamental principle remains. Energy levels are quantized for all atoms. Each element has its unique spectral fingerprint, which we use for spectroscopy. The key lesson from this historical example is how science progresses. It starts with careful measurement of phenomena. Then comes pattern recognition, finding mathematical relationships that fit the data. Next is physical interpretation, proposing a hypothesis about the underlying mechanism. Finally, validation by making predictions that can be tested experimentally. When predictions are confirmed, confidence in the theory grows. This workflow, from measurement to empirical rule to theoretical model to validation, applies across all branches of science, from particle physics to biology to cosmology.